So in our earlier classes, we have discussed about the synchronization problem. Three of the classical problem of synchronization we have discussed. One is producer consumer problem. Second one, producer consumer problem is also known as the bounded buffer problem. Second one, we discussed about the monitors. And third one is the dining philosopher problem. And all these three problems are solved by using some semaphores, right? Or the mutex we have used over here. So although semaphore mutex here is used as the semaphores, but semaphore and mutex are not exactly same. Semaphore is a synchronization, what we can think of a signal, whereas mutex is an object kind of thing. So the semaphore, binary semaphore, we have used there as a mutex. Anyway, so three problems we have solved. The last problem that we have solved is the dining philosopher problem, where we have seen that this can be solved by how using by the weight and signal functions. So before any of the philosopher starts eating, it will put lock on two of its neighbor chopsticks on I and I plus 1 modulo 5. Correct? And when it finishes eating, it will release now both the chopsticks and it will start thinking. It will start thinking. This is the solution that we have made. Correct? So if we execute, if you have this solution for solving that problem, dining philosopher problem, think of a situation. So what you are doing, we are not putting lock on both the chopsticks at a time, because I have told earlier that the philosopher will take one chopstick like this one, it will acquire one of the chopstick, and after acquiring the first one, then it will go for acquiring the right chopstick. This is for the left chopstick and this is for the right chopstick. So these are two different statements. Okay, now just think of, I have a philosopher over here, a process over here, and I have some process over here. This is the process P5, right? And this is the process P2. There are some processes over here, P1, P2, P3, some processes are over here, right? Now, processes are, we can see the philosophers in our case. There are 4, 5 philosophers over here. If the moment P1 wants to, if P1 is hungry, it will try to occupy two of its neighboring chopsticks. When P2 is hungry, it will try to occupy two of these two chopsticks. When P3 is hungry, it will try to occupy these two. And P4, when it is hungry, it will try to occupy these two. And when a particular process will occupy two of its neighboring chopsticks, these two, if it will get, then only he can start eating. Then only he can start eating. Correct? So just think of a situation, all the philosophers get hungry at the same time. All processors get hungry at the same time. What they will do? If all processors are hungry at the same time, what they will do? Every process will execute this code or not? Every process will try to execute this code. Do you agree or not?
Yes, sir.
Okay. So every process will execute the first instruction. Every process will execute the first instruction. So when the first instruction is executed, P1 may have acquired this, P2 may have acquired this, P3 may have acquired this, P4 may have acquired this, and P5 may have acquired this. So all of the process, while executing the first instruction, weight chopstick of I, all processes must have acquired one chopsticks. maybe the left chopstick, left or right, any one of the chopstick has acquired. Now, when each one of the philosopher tries to access the another one, they cannot access. They cannot access because this is being already occupied by the another philosopher. Are you getting me? They have executed the first one. They cannot execute whenever they will go for this one, acquiring this lock, they will be spinning, the process will is in wait state because its neighboring process has not released the chopstick. It is acquiring it. So every process is having one chopstick and waiting for another process to finish. While if they will go on waiting like this, none of the philosopher will be getting the chopstick. They will get hungry and over time they will die. Are you getting me what I'm saying?
Yes, sir.
Because all have acquired one chopsticks. So wait chopstick of I, wait function will put a lock on this ith chopstick for each process. When each of the process is going for the next one, is going for the acquiring the right one, it is being already occupied, so they will never get a lock. So the philosopher will go on waiting like this indefinite period of time and they will never get a lock. So they can't even eat. So this leads to deadlock. So although the solution that you have provided is a reasonable solution, but this fails when all processors get hungry at the same time and wants to acquire the lock at the same time. The solution guarantees that no two neighbors are eating simultaneously. However, there is a chance of deadlock. There is a chance of deadlock. It is ensuring that two are not eating simultaneously. That is true. But this doesn't give a guarantee that it will not, deadlock will never occur. It allows at most 4 philosophers to be sitting simultaneously at the table. Allow a philosopher to pick up the chopsticks only if both are available. So these are the things that can be used for handling that deadlock. So we see that deadlock may occur. So if the deadlock may occur, we'll put some additional condition over there. What is the additional condition? We'll allow at most 4 philosophers to be sitting simultaneously, not 5. Even if 5 are there, only 4 can do the operations. Allow a philosopher to pick up a chopstick only if both are available. What will say? That means if two chopsticks, one philosopher is picking left one, then trying to get the right one. So we'll put a condition that if the right one is not available, you release the left one. Because you cannot eat, so you release the left one. You can't wait by holding the chopstick. Is it understood what I'm saying?
Yes, sir.
So we'll put a condition that if you are not eating, you release that chopstick. So allow a philosopher to pick up the chopstick only if both are available. If both are not available, only one is available, you release the second one. Use an asymmetric solution and odd number philosopher. So we can do in this way also. Odd number philosopher picks up first left chopsticks and then the right chopsticks. Even number philosopher picks up the first right chopstick and then left. So this can also be, this can be given. So first even number, then odd number, in that way also we can give. This is what to avoid the deadlock, because we have seen there are some cases, there is a case in which the deadlock will occur. And to avoid the deadlock, we can do in this way. Correct? There are some problems that may occur in a semaphore as well. What are the problems with semaphore? Incorrect use of semaphore. We know that while entering into the critical section, usually we give before and after we give either wait or signal. Sometimes we change it by giving signal first and then mute, wait. If I interchange this and there is a suppose signal mutex I have given, and in the and after the critical section, I have given the wait mutex. Then what will happen? So several processes may be executing in their critical section simultaneously, because signal operation, what it does? Signal operation increments the semaphore variable, right? So several people will be there in the critical section. It is not checking, it is not a wait over here. Correct? So if you have a mistake in giving this signal and wait in proper order, if you are not giving, then there might be a chance that multiple processes will be there in the critical section. Sometimes the signal operation is replaced with wait operation. First mistake what you have done, if you are using alternatively. Second one, it says you have written correctly over here, but you forget to write signal and you are writing wait over here. You are writing wait over here. So now what will happen? So this is actually wrong, but you have by mistakenly written wait. What will happen? So this has entered into the critical section, and what will happen? And it cannot, the wait, again you have a wait mutex. So what will happen? So it will be in the first the semaphore is decremented and it has entered. The next time again is less than equals to 0, because it is 0. So it is less than equals to 0. It will be there only. So it will never end. It's a deadlock will occur. Are you getting me? What is wait function? While s less than equals to 0, do nothing. Now, if it s less than not equals to 0, then s minus minus. This is wait function. And what is the signal? Is the s plus plus. But you have not used the signal. You have used wait 2 times over here, after and before the critical section. So you have entered by doing s minus minus. So now s is 0. Now what will happen? Again, if you are calling this, that means it is in the wait state. So indefinitely it is actually waiting. It is inside that only, in the critical. So incorrect use of semaphore may lead to some problems. And sometimes omitting of wait or signal or both may also give you raises some problem. If you forget to give wait or forget to give the signal. So both deadlock and starvation are possible in case of semaphore. We cannot give a guarantee that deadlock will never occur or starvation will never occur. Okay. Anyone who can say what is the difference now between this deadlock and starvation? Anyone who can say what is the difference between deadlock and starvation till now, what you have discussed? Anyone who can give a difference between deadlock and starvation?
Sir, if the deadlock occur, then it will remain in the critical situation, whereas in starvation, there might be a chance that it can come out from the critical situation.
Yes. So in starvation, the process is ready to execute, but it is not getting a chance because of high priority or for bad luck. Starvation is the process is ready to execute. Process is ready to execute, but it is not getting a chance because of 2 things, because of bad luck or high priority process, arrival of a high priority process. The moment a process has made a request, at the same time another process will come with higher priority and takes that resource. So the previous process will be in the starvation. So again the process makes a request. At the same time, some other process may not be, the priority is not there. Maybe some other process makes a request and grabs or takes that resource. The previous process is in the starvation. So process may get a resource, but it is not getting a chance. But deadlock says multiple processes are waiting for each other to continue, and the situation is that none of them can continue for indefinite period of time. So there is no chance that they will come out. Correct? So we have seen what are the solutions over here. We have seen about we have used the semaphore, we have used mutex, we have used the what the, the for get and set methods, although it is being hardware method which can be used for solving this process synchronization problems. We have another tool that is used for solving this process synchronization problem is called the monitors. Monitor is a high level abstraction that provides a convenient and effective mechanism for process synchronization. Monitor is an abstract data type which encapsulates shared data variables and operations on a procedure. So what actually this monitor is, if you would have remembered that using a class in Java or in C++, you must have used a class. Yes or no? Class have you used or not? Have you? Okay, inside the class, what you
Yes,
have?
sir.
So inside the class, what you have? Inside the class, you declare some data members, you declare some member functions and methods. Then what you do? You create an object of that class, and through the object, you can call which one? You can call only those procedures which are there in the public, right? And those procedures can have access to the private members or another protected members. Similarly, over here, by exactly simulating the same thing is being applied for solving the synchronization problem over here. We'll take a abstract data type where we'll keep the shared data variables and the procedures, and we can access those through some special kind of variables. So that construct is known as a monitor. It is an abstract data type. Class is abstract data type, structure is abstract data type. So monitor is also abstract data type. So what is a class? Class provides two things. One is data hiding or data encapsulation is also provides. Here monitor is also a kind of encapsulation. Is a kind of encapsulation. Encapsulation is what? Binding of data and methods in a single unit. Here also binding of the data size, shared data and procedures in a single unit. I'll give the example. For the time you remember, monitor is just like a class where you will have some data members or variables or shared data variables we say, and some procedures. So procedures are functions or methods that you say in Java. So now we'll see how the monitors will be helpful in solving our problem. As this resembles to our programming, therefore monitor is being used widely for solving this process synchronization problem. This is being implemented in Java, in C++, in other languages as well. So see over here, the monitor is an abstract data type which encapsulates shared data variables and operations or procedures. So what is there? It encapsulates what? Shared data variables. It encapsulates shared data variable and operations or procedures. You think of this as shared data variables and procedures. Like in a class, you have variable, data member and functions. You have shared data variables and procedures. So shared data variables that are to be shared by all the processes. Shared data variables that are to be shared by all the processes. It contains a set of programmer defined operations that are provided mutual exclusion within the monitor. What is mutual exclusion? Mutual exclusion is what? Mutual exclusion means no two processes can have access to the same variable, same data at the same time. No two processes should be, no more than one process cannot be in the critical section. So monitor is supported by programming languages to achieve mutual exclusion between the processes. Right? So this is supported by programming languages like in Java, C++, it is being so programming is supported program like to achieve mutual exclusion between the processes. Like the Java synchronized methods Java provides wait and notify constructs. A procedure defined within a monitor can access only those variables declared locally within the monitor and its formal parameters. A function can access which one? Only the variables inside that class. If you could remember the class declaration, one method or data or a member function can have access to which members? Only the data members of that class only. So see here also a procedure defined with monitor, a procedure defined within a monitor can access only those variables declared locally within the monitor. So the procedure can access what? The procedure which is inside the class can access what? Those variables which is there inside the monitor and the formal arguments. Is it understood or not? Is this slide understood? Or any
Yes,
doubt?
sir.
Okay. So let us take an example over here. It says that this is the encapsulation we can see. This is a class, for example. We have a portion where the shared data, where variables are being stored or shared data over here. And all procedures are stored over here. All the procedures are stored as this is a procedure 1, procedure 2, procedure n is being stored. These are the operations to be performed. And like in a class, you have a constructor. Similarly, you may have a initialization code. A part of the monitor may be used for initialization of the data members. Correct? Just think of it is how much it is resemble to a class. Class has data member, methods, constructor. Here I am saying the class has shared data, procedures or operations, and a code where the data members may be initialized or initialization code. This is the entry queue outside of this monitor where the processes will enter. So one process can have access to this procedure at a time, or to this monitor at a time. Correct? Now, what is the syntax of a monitor? What is that? What is the way the class is defined? Class, class name, then data member, then procedures. Here also monitor, monitor name. You write their class, class name. Here is monitor, monitor name. Then you declare some variables over there. Here also will declare some variables. Shared variable declaration. We have some variable declaration. There you declare some methods. There you declare some methods. Here also will have some methods. So data members we say. Here also you have some data members. Sorry, data methods, member functions. Correct? So there you write class, class name. Here you are writing monitor, monitor name. There we have some, in Java we use some variable declaration in the private section. You do not have private, but it is there inside the monitor. It will be accessed as a private. And you have some functions are there, and here we say some procedures, meaning is same. And besides that, you may have a constructor. Here we say is the initialization section where the variables are initialized. Those shared variables are being initialized. So what will happen, as this is encapsulated, no outer object of monitor class can only have access to these procedures. So we have a restriction that every process that wants to access these variables has to go through these procedures. They cannot have direct access to these variables. We have a restriction over here. A object of the monitor class, any object of the monitor type can have access to the procedures. However, procedure can have access to the variables. So monitor ensures that only one process at a time can execute code inside the monitor. So this will ensure, monitors ensure that only one process at a time can execute code inside the monitor. No two processes can enter, right? But it is not powerful enough to model some synchronization scheme. There are some synchronization scheme which which may not be solved by the monitor. Correct? So this solution, this monitor solution is a abstract data type kind of thing. It is abstract data type where we have some shared variables, we have some procedures and a initialization code. So this monitor can be accessed by one process at a time by putting them in a queue, and that we say as the entry queue. Is it understood up to this? Is it understood up to this?
Yes, sir.
Okay. Now it says that in the monitor we may have some condition variables. What is this condition variable? I will tell you. The condition variable provides synchronization inside the monitor. Inside the monitor, just think of an example. For example, I will say this is a monitor. This is a monitor, and I am having a producer-consumer problem. We have some shared data. We may have some shared data over here, right? We have some shared data which will be accessed by either by a producer. It will be accessed by a producer or by what? Or by a consumer. It will be accessed by a consumer or through a producer. Is it or not? So what they will do? They have to have a set of procedures over here. They have some procedures over here. So each of these will execute some procedure to access these data, shared data. Is it or not? This is the monitor. Do you agree or not?
Yes, sir.
Okay. Now what happens? Now whenever we access these procedures to access this data, and we ensure that either the producer or the consumer should have access to this monitor. So we are actually, the synchronization is, we restrict it outside of this. The synchronization outside of the monitor we are doing. Just think of consumer one. Suppose no item is produced. You hope you must have remembered the producer consumer problem. Producer produces, consumer consumes. Now suppose there is no item is produced and consumer enters first to the monitor. What will happen? The consumer enters into the monitor by invoking what? The wait function, for example, because we have a procedure over here to produce and consume. So while consume, it will go over here. No item is found, but it has changed the monitor. It has put a lock inside. Do remember how will you know that either the producer or consumer will go? You have to put a lock over here. Are you getting me? There is a monitor inside which you have shared data, some procedure which will be accessed by a producer or consumer. And we want either the producer or consumer should go. That means whoever will go, it will put a lock and go. Otherwise, how the synchronization will be there? Is it or not?
Yes, sir.
Okay. So if producer will go, it will put a lock, access any procedure. If a consumer will go, it will put a lock, then it will invoke a procedure. Suppose the consumer will move and put a lock over here. The consumer will go and put a lock over here. That means no producer or consumer can enter now. So consumer will go, put a lock, but found that no item is produced. No item is produced. Nothing is there. So it will wait. Why it will wait? Because the item will produce and it will take. Because that is written inside the consumer code we have written. That wait for this. If it is there, then it will decrement that number of full number of full and number of entry will increment, number of empty will increment, the number of full decrement, that operation will do. But nothing is over here. So as nothing is over here, it will be spinning in this because that is nothing. So it is spinning over here, but it cannot release this because item is not available. But at the same time, can a producer enter into this monitor? It cannot enter. Why it is there? Because the lock is already put by consumer. So there are some situations where the externally what we are doing, externally we are controlling by putting a lock is not enough. We have to have some mechanism inside this monitor, So that mechanism is given by some conditional variable, these are condition variables. What are these condition variables? The condition variables will have some predefined methods. I may have a number of condition variables. So condition variable provides synchronization inside the monitor. So previously lock we have put outside of the monitor. Now it says we can have synchronization inside the monitor can be through condition variables. So each region the process waits, we need one condition variable. For every region the process will wait. Any region, may the consumer process will wait or producer process will wait, we need one condition variable. Right? How will you declare the condition variable? We will declare like this: condition x comma y. So x is a variable, like we write integer xy. X is of integer, y is integer. So if I have 2, 3 condition variables, I will write condition x, condition y, condition z. What are these x, y, z? There might be multiple reasons for which it has to wait. Like one example I have given over here. So if a process wants to sleep inside monitor, if a process wants to sleep inside monitor, allows a waiting process to continue, in that case, condition variables are used. What is the example that I have given? The consumer is sleeping over here. The consumer is sleeping or the producer is waiting. In that case, what we will do, the condition variable will help us. What the condition variable? There are two operations. There are two operations allowed on a condition variable. There are two operations allowed on condition variable. What is that? Condition variable dot wait or condition variable dot signal. Condition variable dot wait or condition variable dot signal. So if I write wait function, what will happen? This says that a process that invokes the operation is suspended. Whoever is invoking this wait function, suppose a particular consumer or producer is invoking this x dot wait, that means a process that invokes the operation is suspended. So what it will do? It will sleep and release the lock. That means if consumer is invoking x dot wait, it will go to sleep and it will release the lock. Once lock is released, that means another process can enter. So it will sleep and release lock until x dot signal, until it is being given the x dot signal. Correct? Similarly, x dot signal, what it will do? It will resume or wake up, because there are some processes might be sleeping over there because it has the item resource not found, it is waiting over here. So it resumes or wake up one of the process that invoke the x dot wait. Because of the x dot wait, they have slept. This is in a sleeping state. Because when we invoke the x dot wait, the current process will go to sleep and release the lock. So how it will be woke up? By using the x dot signal. So that this, which is earlier it was invoking x dot wait, it was in sleeping state, now can be woke up. And lock is automatically passed to the waiting process. If none of the process is waiting, if no x dot wait on the variable, then no effect on the variable itself. Is it any doubt over here? Try to understand. if you want to synchronize this inside the monitor, we need condition variables. Condition variables has two operations, wait and signal. For example, in our case, what the example that I have given, consumer is waiting over here to item to be produced, but it will wait over indefinitely. To solve that, what it will do, it may invoke the x dot wait. It will invoke the x dot wait so that this will go to sleep and release the lock, so the producer can produce. And after that, the x dot signal can be called so that this can be active. Is that understood?
Yes, sir.
Okay. So these are some situations. It says that if process P inbox x dot signal and process Q is suspended in x dot wait, what should happen next? Suppose one process P, it has invoked x dot signal. X dot signal is this one. It resumes one of the process, which is there in which has invoked the x dot wait. So what will happen? Any one of these will be allowed. So both Q and P cannot execute in parallel. If Q is resumed, then P must have to wait. If Q is resumed, then P must have to. So if Q is earlier suspended, it may be given permission to resume. At that time, P must have to wait. So what are the options that we can include over here? We may include some options with the condition variable that either it will signal and wait, or it may signal and continue. So that means it will give a signal and wait. So P waits until Q either leaves the monitor or it waits for another condition. Signal, there are two things can happen. Either it is a signal and wait. So the process P will wait until Q either leaves the monitor or wait for the another one. P has to wait. And if it is signal or continue, if you are using, then Q has to wait. So these have both has pros and cons, both has advantages and disadvantages, and a language implementer can decide that which one to be used. And the monitor implemented in concurrent Pascal Pascal is a language which uses this. So we can have different way. This can be either it is a signal and wait form, or we can use in form of a signal and continue. Right? We have different languages. This can also be implemented. It is given. Other languages, it's not only for this Pascal, it can be on other languages as well. Correct? So condition variables, it synchronizes inside the monitor, and it has two functions, signal and wait. Actually, it has three functions, but in your book it is given two functions, wait and signal. It has wait, signal, and broadcast. It will it informs all the waiting processes. Three operations: wait, signal, and broadcast. So anyway, the major operations is wait and signal. So wait and signal operation it does. Correct? So if you look into the semaphore versus monitor, if you want to compare the semaphore versus monitor, the difference, the basic difference is that semaphore is an integer variable, whereas monitor is an abstract data type. Semaphore, you know, it is an integer variable, right? If binary semaphore is having 0 and 1, if it is a counting semaphore, then it's an unrestricted domain, it is an integer only. And but monitor is an abstract data type. Like a class, it is a abstract data type. What is the action of semaphore? The value of semaphore indicates the number of shared resources available in the system. If you recall the read count that you have used in reader writer problem, every time a reader enters into the critical, wants to enter the critical section, read count increments. So that is actually a is a counting semaphore, and from that only we could know that how many readers are present in the critical section. So the value of semaphore indicates the number of shared resources available in the system. But what in monitor, what you have, the monitor type contains shared variables and the set of procedures that operate on the shared variables. So in the monitor type, what you have some variables and some procedures. Those variables are binded together. And for the semaphore, when any process accesses the shared resource, it performs a wait operation. It performs a wait operation on S, and when it releases the shared resources, it performs the signal operation. This you already know. Whenever you are using a semaphore, you want to enter you want to access a particular resource, you will put the wait, get the resource. After that, you release it. So critical section to enter into the critical section, before that wait, and after that signal. But in monitor, what you have, when any process wants to access the shared variable in the monitor, it needs to access it through the procedures only. The data members or shared data cannot be accessed. Correct? And condition variables are not there in semaphore. Semaphore doesn't have condition variables. But the monitors has condition variables. Condition variables are used for what? For synchronization inside the monitor. Inside the monitor, because outside the monitor, you can use some locks. You can use some lock for, but inside the monitor, if you want to synchronize, then you have to go for condition variables. Let we want to solve the dining philosopher problem by using a monitor. Example will this example will tell you that how this monitor actually works. Look into the solution. You must have remembered the dining philosopher solution. Whenever a process would enter into the critical section or eating state, it has to put lock on two of its neighbors. It's I and I plus 5. If 5 philosophers are there, I plus I plus 4 modulo 5. In that way, actually, it puts the lock. Just see over here. Look into this code. What you are doing over here, we have some variables and methods. As I told, a monitor, this is monitor and monitor name. A monitor has some procedures and shared variables. So procedures are what? This is one procedure. Pick up is one procedure. Put down is one procedure. Correct? One is pick up, second one is put down, third one is test, right? And I have told you that there might be a constructor, so it's a kind of thing, initialization code. So inside the monitor, we have 4 procedures, out of which one is the constructor or initialization code. We call here as initialization code. Correct? Very simple to understand. The same problem I was just writing in form of a class. So I have a constructor in which, so what is the initial state for everyone? If 5 philosophers are there, they spend their life by thinking and eating. So at the initial state, they are not eating. Initial state, they are thinking. So in the initialization code, we have written that for I is equal to 0, I less than 5, I plus plus, state of I is equal to thinking. What is state of I? State of I, look over here. What is the state of I? The state of I can be thinking, eating, or hungry. Actually, I told you 2 things. One, they spend their life by eating and thinking. This is true. But before eating, the state is over here, we have defined it as hungry. That means before acquiring the resource, we must know that it's going to request. So that state we put it here as hungry state. So if I declare, we have this is the shared data members. We have a enum data type. this is defined in that enum of state of 5. That means state of 0, state of 1, state of 2, state of 3, state of 4, and state of 5. And out of these 5 states, any one of these value can store. So 3, 4, you may have 1, 2, 3, 4, 5. I have 5 states. So state of 0, state of 1, state of 2, like that it will be there. Correct? Now, what I can put over here, I can put some, either I can put thinking, or I can put eating, or it may be hungry, or it may be hungry. Any one of these. Either it may be hungry, or eating, or thinking, like this. Is it understood? These are the 3 states of the philosophers. Now we want to solve it by using the monitor. So I use a monitor. Monitor name is dining philosopher. I have some variables over here. State of 5 is a condition enum variable, and we have taken 5 condition variable as well. Condition self of 5. Like in your example, I have given condition x and y. Here you have 5 condition variables: self of 0, self of 1, self of 2, self of 3, self of 4. So we have 5 condition variables. So what the pickup is doing? So it makes that particular process. Suppose somebody wants to pick up. Pickup means he is hungry. So state of I is hungry. We check for the test of I whether it is available or not. So it checks the test of I. It calls this method. It checks that whether the chopsticks are available or not. That means if the I plus 4 modulo 5 and state of I is hungry and I plus 1 is 5 is eating. If these two are eating, means if so not eating, if the 2 of its neighbor are not eating and this is hungry, then what you will do? We'll change the state to eating and we'll give a signal over after this will give a signal over here. What does it mean? If somebody wants to take a chopstick, he is hungry, he should be a hungry state. 2 of its neighbor must not be eating, so that we'll allow the process for eating. So till the time we'll put the log that if it is there, the self dot if state of I is not equals to eating, so we'll have eating over here and self of I dot signal. Correct? So after that, when it comes over here, it checks that if it is not eating, so what is the state we have done? Eating. So if it is not eating, then wait. So when it is finished, it will put the wait. It will invoke the wait over here. Correct? Similarly, while putting down, it will change the state to thinking and it will invoke the test for both of its. Now what you have done, the code we have written in form of a class, the data members are taken over here in a variable. We have some procedures and some condition variables. Correct? Similarly, so what you have done, look over here, this is before eating. What you have done is a dining philosopher pickup of I, and releasing will have dining philosophers dot put down dot. What is dining philosopher is the monitor name. I just have to write this the same. So this ensures that no deadlock will not occur because we are using a monitor over here. Deadlock will not occur. Starvation may occur because every time a particular process may get a chance. So similarly, the solution that you have provided for dining philosopher, so same monitor solution for producer consumer is also given. We have some variables over here. Variables we have taken. We have some procedures, same procedures that you have defined inside the class and the condition variable. And this is the proper monitor name. Correct? So this is all about the monitor, and we have left with this. There is an important topic left over here is the deadlock that we'll discuss in the next class. The deadlock is a big topic actually. So that we'll cover maybe in the next class. So any doubt up to this? Anyway, I'm just taking the attendance. In the meantime, if you have any doubt, you may ask. Okay, I'm just calling the absentee roll numbers. Roll number 2, 18, 20, 22, 25, 27, 30, 34, 37, 39, 51, 52, 73. Okay, so any doubt now? If you have any doubt, you may raise your question now from today's class. Okay, so thoroughly go through those slides, and the next class will start with this deadlock. So with this, I'll end the meeting now.